actually do something. I'm not sure if that popped up on your screen or just mine. So what we want to do is basically make these molecular movies. And here I'm going to describe our wildly successful experiment, biocars, but I won't tell you the results because they're not published yet. I have 87 slides, and I want to hopefully cover those in probably the next 20 minutes. So first I'm going to do the thank yous. Oh, did my computer? There we go. So I started off working with Robin Owen and Danny Axford at I-24 at Diamond, and we did a lot of experiments with them. I'll cover a lot of this. I worked with the Dwayne Miller group. We did XFL experiments at the LCLS as well as SACLA. I did some very successful experiments, mostly because of the hard work of Mike Huff and Dr. Strange. And we did experiments with Ilma Schlittling as well at SACLA, and there's some hilarious fails from that experiment that I'll tell you a little bit about. And so the Diamond team were phenomenal, and where I cut my teeth for serial crystallography. The Canada-German team of Dwayne Miller, California's LCLS, and the amazing work by the Japanese, especially Sugeki Owada, and the Essex team, Mike Huff, Dr. Strange. And obviously, I got a job at 19ID, and so we've been based out of here for the last 3 years. I'm gonna do a little bit of history about myself, so you have some idea about why I have an English accent, but I work in Chicago. I'm not sure how much of the screen you can see. For me, the right-hand side is cut off by images. On the right-hand side, there's the UK, where I went to university. And then I worked in a summer camp in upstate New York when I was like 18, 19, 20, and 21 in the summers. I did my year abroad in Florida, where I met my partner, which started my long relationship with America. And we moved to America after my undergraduate degree. We then drove to California, where I got my first job at the ALS. And I didn't know what a synchrotron was at the point. I was working in a burger joint, flipping burgers with an undergraduate degree in physics. And I landed a job as a beamline engineer, luckily, because of a long story. And then I eventually went to do my PhD in Canada. I didn't actually go to live in Canada because they didn't have a synchrotron. They were still building the CLS at the time. So my research was actually at the ALS. And then the beamline I was working at was uniquely bad for my personal experiment. So Ina Cohen down at SSRL was taking all my data, and I didn't even have to travel from Berkeley down to Stanford. And then I realized I didn't have to live in California at all. So we moved back to the beach in Florida, and my data was being taken in California by Ina Cohen, who's a fantastic group leader there now. And I would fly backwards and forwards from Canada to the beach in Florida during my PhD. I eventually got my PhD and moved to the UK, and that's where I started working with Robin and Danny and that whole group, and started this whole serial crystallography business that we're involved in now. And eventually I wanted to move back to America. My partner's American, and so we wanted to live over here. And eventually I got to my current job at the APS. So I'm sort of broad in my worldwide sort of synchrotron experience. And so if you have any questions about dealing with different synchrotrons, I can probably answer those. This is the only bullet point present slide of all 87, and this is sort of why do you do serial crystallography? And these are the reasons, basically. But the long and the short of it is that we want to do structural dynamics now, really. That's what we want to do. And so we're searching for ways of invoking change in proteins while they're still in crystalline form, and sort of watching them as they develop. It's also good for low dose stuff as well. This all started with the Dwayne Miller group. They had a graduate student making silicon chips, and each of these silicon chips had like thousands of wells in them, and inside the wells, you put the crystals. And this is one of the silicon chip images from there. And you can see that it's not perfect. We worked against these imperfections at the beginning. So everything starts off rough and then gets better over time. This is a great microscope image, and you can actually see myoglobin crystals at the bottom of these little wells. And the wells have these little holes, so a lot of the liquid is drained away, and they sit there, and then you shoot the X-rays through the wells, through the bottom, and then capture the diffraction at the top. And here you can see the myoglobin in one of the chips. This is just a subsection of one of the chips. So serial crystallography, just as the short version is, in normal crystallography, you get a single crystal when you rotate it, and you take thousands of images from a single crystal that's kept at cryogenic temperatures. For serial crystallography, it started with X-FELs, where the X-FEL would blow up every single crystal, so you had to deliver get one image from thousands of different crystals, and that way you could build up your diffraction patterns and eventually figure out the structure. So you need thousands of crystals and a single image each. At Diamond, we developed these chips made by professionals, the same people that developed all the ARM silicon chips, and they were experts in lithography, and it was a serious improvement in the quality. And we worked together with Germany. So this is the Diamond Hamburg chip, I think it's called. And we worked closely together. And you can just see the difference in the quality compared to what I showed you earlier. And they depending on how long the silicon chip was left in the acid bath, you could adjust the size of the aperture at the bottom of this well. And they were the precision was just unbelievable, really. Diamond had a lot of money, and it still does, for things like animation and equipment. So will this run? Excellent, it will run. Hopefully you guys are seeing this. So Diamond made these really good animations, so you can see, how this is actually sort of how the crystals end up in the bottoms of the wells, and there's a slight vacuum that pulls excess liquid away. And then the chip is covered on both sides with mylar. This is the Diamond chip holder that we developed. This is where the story for the nylon mesh holder starts. You see this silver aluminum mesh chip holder. I bought a bunch of chips for argon, and I still have them on my shelf over my right shoulder here. But I couldn't get my hands on a holder because the lawyers in America said the holder wasn't patented, so I could just have one or make one myself. And I didn't want to make one without annoying Robin and my friends in Germany. And I was like, I just want a MOU, basically, a memorandum of understanding. And the lawyers were like, you don't need an MOU because it's never been patented. You can just have one. And if an MOU would be redundant and would expose us to whatever. So anyway, this is a slide from 2.5 years ago when I thought I could get an MOU. I'll speak more to why the nylon mesh holder came about in just a bit. This is another one of the Diamond animations. Basically, you can see that you're rastering, basically sort of plowing the field as you go through these windows. And there's a crystal in each one of these, and then you get a diffraction from each one, and then you build them up. And the Diamond chip has 25,000 wells in it. This is one of the older chips. But you can see, this is just a nice animation, so you can see that you can stay within the hole. So the precision of the stages is good enough to keep within submicron accuracy. This one is not well aligned. You can see that the hole drifts relative to the arrow. And they can go extraordinary speeds. This is one going at 106 hertz. And what you have to appreciate about this video is for a good period of this video, that chip is not moving. It stops for every single one of those windows. But it's so fast, it's inhuman how fast these things can go. And if you think that's fast, the European X-FEL now can do like megahertz crystallography. So you cannot do megahertz crystallography on fixed target. This is fixed target serial crystallography. It was designed to go 100 hertz for LCLS or 120 hertz for Swissfel or 60 or 30 hertz for SACLA, but the European X-FEL does tens of thousands of hertz, and that they have to use injectors for that. This is just an idea of, you can see where crystals diffracted. So each one of these is, it tells you whether a crystal was in that well and whether it diffracted. And then you can sort of map this out over the chip and see, where your crystals landed. So the first experiments we did with the Miller team out of Canada and Germany was at LCLS. LCLS made this really nice video. So you can see that this is them blowing up water droplets. This is, strobed, and you can see that basically you have to deliver a new crystal to each position because the X-rays will completely obliterate your crystal. And this is what started the whole serial crystallography business. I also did work at Sackler. This is my favorite video. If you're wondering whether doing science in Japan is more interesting than doing science anywhere else in the world, the answer is yes. And they have this, I won't show the whole thing, but this video goes on for, I think, 1.5 minutes. And there's a whole backstory about, you know, their supercomputer and someone coming back from the future to help create synchrotrons so that they can, anyway, it's a phenomenal short animation by the Japanese. And the culture shock for Japan was quite interesting, actually. This was one of the web pages for Sackler. And you can see this character in the corner, Pico. We actually contacted Japan because we did an experiment there. We wanted to know how much space we had to work in, the wavelength, the, you know, sort of how far away the sample was from the detector, and like, you know, the envelope of space we could work in. And they hilariously sent us a link to this web page to explain to us how Sackler worked. And it was sort of this sort of whole culture shock. And we thought, this can't be right, that they, you know, but it is just a culture. And if you think Pico's just nothing, Pico's actually on the doors in Sackler, and there's like proper, you know, documents with, you know, technical drawings that have like Pico in the corner. And it's just an entire, and you can see she has, you know, magnifying glasses for eyes. And it's just, Sackler was phenomenal. I actually love Sackler. It's one of the most amazing places I've been. This is Danny at Sackler. So this is just the history of us working, getting serial going. The laser burned a hole in our camera. All kinds of crazy stuff happened there. This is quite interesting. So if you see this hole on the left-hand side, this is the high EV, like 12K EV, the XFEL laser from Sackler burned a hole straight through 500 microns of silicon. And if you think that was bad, we did an experiment with Ilma Schlittling where they set the EV, I think, to like 8K EV, and it completely destroyed the chip, which is super embarrassing when 20 people fly to Japan and they want to use your equipment, and then everything literally falls apart. And you've only got 30 of these chips. The idea is to wash the chips and then reuse them. And then every time you put one up, it basically turns into dust. And that was, yeah, I felt like a weird combination of embarrassment and just sort of horror. I think that was quite a trip. But back at synchrotrons, we did some work with Diamond, and serial has some interesting side effects that you don't really expect and would never see with a single crystal. So this video, this is basically, instead of plotting whether a crystal diffracted, this is the unit cell volume for each crystal in each of the wells. And then each crystal was shot, I think, 15 times in a row. So its dose increases over time. And this is us watching each crystal dose increase, and but you're visualizing the unit cell. And what you actually see is it goes from blue to brown with that, and most of the time skipping green and yellow. And what this turned out to be was the unit cell actually changed size during the experiment. So there were two unit cell sizes, one where it was not so warm and one where it was a little bit warmer. Or we weren't drier, we're not sure exactly what the change was, but the change in the unit cell was a small loop at the edge moved a little bit. And so the whole unit cell changed shape. And you can actually plot this, and you would only see this with serial. You would never see something like this with regular crystallography. And you could actually watch the diffraction patterns, and there would be a diffraction pattern, and then there wouldn't be a diffraction pattern, and then there would be another diffraction pattern. And it was like, because when it was changing unit cell size, it would no longer diffract because mathematically it was no longer obeying Bragg's law. And so you could actually watch this. It was scientifically completely uninteresting, but absolutely fascinating and a mind-boggling experiment, actually. But what that experiment led to, is originally designed, was to see whether we could monitor radiation dose. And here you can see, this this work with Mike Huff and Strange and Robin and Danny at I-24. And then, so this was a myoglobin, I think, or hemoglobin, I can remember now. And you can see the water molecule gets further and further away the more radiation the protein gets. And then Sackler, which is essentially a zero dose. So another side effect of XFELs is the crystals diffract before they blow up. So it's like lightning and thunder. So you see the lightning and then the thunder blows up your crystal. So essentially your crystal gets no dose. You don't have any radiation damage. And here you can actually plot the water's distance from the heme. And you can see that you can kind of do a zero dose extrapolation. So you may not, for some certain experiments, you may not need to go to an XFEL. You can do a synchrotron experiment and get information, or extrapolate to what you think an XFEL experiment will be like, especially with radiation does. This is completely unrelated to anything, but it's a very cool experiment we did at Diamond. I just want to show you this just to keep methods and ideas of crystallography, of crystal delivery in mind. This is an acoustic drop delivering droplets onto a mylar. I hope you all can see that. It's a very cool technique that's been developed. I'm not sure if it's in use for anything yet. I hope so, because it looks phenomenal. So back to the APS. So I moved here 2.5 years ago. The APS upgrade is in about another year and a half, and the APS upgrade is going to make a very small, very bright spot available. And this is going to be nearly perfect for serial crystallography, because being able to do multiple crystals, there's another idea that if you shoot crystals at 35 keV that are about 5 microns or less in size, a lot of the radiation damage will be ejected from the crystal itself. And so you'll be able to do really sort of low radiation damage, multiple crystals, and just really plow through serial crystallography. And so APS should be an excellent machine for doing time-resolved synchrotron work, especially as it relates to crystallography. So 19ID is not, we don't have a laser. BioCars has the laser for the pump probe. And so initial experiments were done at our beamline 19ID. It started because I had history in serial crystallography, but also when I got here, Georgie had these unbelievable, I don't know if you can see the right, can you guys see the right side of the slide? Georgie was producing these crystals in droplets, these microfluidic droplets, and it just blew my mind that you could grow crystals in droplets. And Georgie was having a terrible time trying to shoot them at the beamline, and I had yet to develop anything at the beamline. So we shipped them off to Diamond and had Diamond put them in their silicon chips, and that worked greatly. And there's a paper coming out about that. Diffraction was fantastic. But that's still not 19ID, that's Diamond. So we were at Diamond, we got the silicon chips, and you can see in the bottom, my chip holder is just this plastic thing held together with, I don't know if you see my mouse, held together with paper clips, basically. But, oh, it left the volume on. I apologize. So this is a 18 hertz. These motors make an absolutely awful noise. And this is 100 millisecond dwell time in each position. Now, yeah, you can see the paper clips much better here. So yeah, this is, I don't have a chip holder yet, a silicon chip holder. I still don't, working on it. So this is us working on the bench. This was actually the first serial crystallography grid scan at 19ID, where I had to hand write down the position of each place that the pin went, and then I counted the spots for each diffraction. And this was like, after coming from Diamond and then Sackler and all that, and then doing this by hand at 19ID was pretty hilarious. But this is the honest to God first serial crystallography at 19ID. But then Georgie did this other wonderful thing, which is he realized you could get this nylon mesh, and his droplet crystals would sit perfectly inside this nylon mesh. And then I realized this was a way better use of space than the silicon chip. The silicon chip, you had to go exactly to these positions and you couldn't miss them and you had to be perfect every time, which wasn't really required for synchrotrons. What's required for synchrotrons is just to shoot everything. And if you could find a way of immobilizing, we thought about spreading LCP on Mylar back at Diamond, and that's good. But if you don't have, if your crystals aren't suspended in a thick liquid, then they move around all over the place. And if you put them between two thin pieces of Mylar, it's like watching a really fast river. And but this nylon turned out to be fantastic at immobilizing not only these droplets. Oh yeah, this is the first proper serial experiment where other people needed to come and watch. But this is, you could use this nylon mesh to immobilize these batch crystals. And here you can see this is a typical sort of batch crystal being just prevented from moving. Basically, the mesh acts as a way of immobilizing it. And then between the two thin Mylar sheets, it has nowhere really to go. It's not great for radiation damage experiments. If you want to hit the same crystal multiple times, you still want a silicon chip for that. And I have plans for the silicon chip. But this nylon mesh is great. It just immobilizes them, and then you just literally plow the field and just shoot absolutely everything. You don't miss. You move one beam width over each time. And right now our beam width's like 50 microns. And so we do 50 micron or 75 micron steps. This is a video. Again, I apologize. I left the sound on for this video. Yeah, and we just shoot everywhere. The beam isn't the smallest or the brightest. It's one of the smallest and one of the brightest for APS, but we're not at that 5 micron, 10 to the 13 photons per second. So Alex, which is the advanced lightweight encapsulation for crystallography, is basically our nylon mesh holder. And we developed this, and I thought it was going to be just like a nylon mesh holder, something very simple, but then the person that actually developed it, Alex Labins, I named it after Alex because he did some really great engineering around it. And this is a picture of it. It's hard to tell. I have videos of it in just a moment, but we have a patent out. That doesn't mean you can't use it. Just call us and you can print it on your own 3D printer. We'll send you everything you need, but it does have a patent. We're required by APS to actually, if we come up with an idea, we have to patent it, which was a whole nother process. Another situation with lawyers was rubbish. But the print was actually fantastic. And here we redesigned our end station so that it would fit neatly on a normal goniometer. And we put our XYZ stage on there. So there's no difference now between loading regular cryo pins and loading an Alex holder. So we can switch between cryocrystallography and serial crystallography within a couple of minutes. Okay. These are some videos I made a while back. So the good thing about the Alex holder is this part. It's two different pieces of plastic, one flexible and one hard. And they're joined together by heat in the dual extruded printer. And this is like 5 cents worth of plastic. And then Alex produced this, so it's got this like ring seal that we just put 4 little magnets on. And then that little ring protrudes, and that's the part that actually seals the 2 Mylar sheets together. There'll be some magnets on the other side, and that ring is pulled towards the other magnets, and that seals the Mylar, which we didn't have for the Diamond Hamburg chip holder. We used screws and like rubber seals, and it was a bit of a pain. This is the other half. You can just, this is me just showing you the trough where that rubber seal, this also is dual extruded. It's got that thin sort of, it's called Ninja Flex, the soft stuff. It's Ninja Flex and PLA, I think. It's not nylon, I think it's PLA, and then these two go together. This is me very crudely showing you how, so this is your 6 micron Mylar. Usually that's put on there a lot neater, no crinkles. That's the nylon mesh with the 60 micron holes in it. And I'll show you a professional doing this. This is me just demonstrating how this system goes together. It's very simple, it's very cheap. It's very low-fi, but the good thing about it is it works, and you can just do it over and over and over. One of the good things about serial crystallography is that you can just do the same experiment more to get your results. And that's got another piece of mylar, so you're going to make a a nylon mesh sandwich between two sheets of mylar. Then that sticks to the opposing magnets on the other side, and then you have your little window, and then that is good to go. And one thing I do like about this system is you can undo it. It's very easy to undo. I'll let you watch that. And that Ninja Flect has a sort of adhesive quality to it for the mylar, which is actually super useful because that 6 micron mylar gets very staticky and is hard to control. And if the Ninja Flex loses its stickiness, you just wipe it with water and it becomes sticky again, at least in regard to mylar. I think this is just a, oh yeah, this is our beamline blowing holes into, like, making gas inside one of the liquids inside the mesh. And you can see the mesh isn't lined up horizontally and vertically. We just literally put it in whichever way it comes and shoot absolutely everywhere. Oh yeah, so 2020, so we did a serial COVID experiment. Enough about that. Okay, moving on to biocars. But maybe not biocars yet. So this is the chip sheet. Basically, it's like a birth certificate. This started at Diamond as well. Like, we give every chip is given basically a birth certificate, and you say who did it, when they loaded it, what's on it, what the molecular replacement PDB is. You know, if you're doing a timing experiment, you put all that information on it, and then we keep those as a paper trail. This has turned out to be one of the low-fi but sort of best things we ever did. Okay, so this is a serial experiment, a precursor to biocars. So I'm not going to tell you what the protein is because I don't have permission to do that. Basically, you can see these two yellow spheres. Those are the zincs. And what actually happened with this crystal is we had this crystal, and then we did a serial experiment, and it had zincs in it. And then we got these crystals, and we washed them in EDTA. I say we, Mateusz Wilimowski from Poland. He's amazing. You'll see him in just a little bit. So we had these crystals that had zinc centers, and then we got these crystals and we shot them with serial. We got the structures, and then we got these crystals and washed them with EDTA, and then we shot those and we showed that we had removed all the zincs. In fact, the zinc in the distance, we actually have two structures. One where we didn't get quite all the zincs out, and then we had this, and then we got a structure where all the zincs are removed, and then we got zincs in cages. And the cages release the zincs under UV, and then we have a structure with no zincs in it that we know has cage. And then we have a structure with zincs in it where we took the zincs out, put cage zinc in, and then lit the UV light over the crystals, the whole batch of crystals, for like an hour. And then the zincs decaged, and the zincs went back into the zinc positions in the proteins. So we knew we were ready for biocars at this point. So we have shown that we can take zincs out. We have shown that we can put zincs in cages and put them in the crystal, and that they don't go to their places until we've decaged the zincs. And then we decage the zincs and we show that the zincs go there. So we're ready, at this point, we're ready for biocars, because biocars has a really bright laser which will decage these zincs super fast. And then in this mix, we also have, which I haven't told you about, we have a substrate. So the idea is we decage the zincs go into position, and then the substrate's like, oh my God, the zinc's there. And then it goes into the active site and does its business. And that's the movie that we're looking to make. And that's what we did at biocars. Oh yeah, I should show you that. This is Mateusz. She's a professional. Look how nice his mylar's dead flat. It's got a big piece of nylon mesh there. So this is how to do it properly, not the video that I showed you. So he's putting on the second piece of Mylar here, nice and flat. So there's no air pockets in there. And he already has the magnet and the top part together, and he just drops that on, and it's a much nicer, he gets a much better seal, I think, that way. And you're done. And then you basically just cut off the excess Mylar. You can see in the background there, he's got metal scissors. We've upgraded to ceramic scissors because cutting that Mylar with metal scissors next to magnets is a pain. So we upgraded to ceramic scissors. So this is BioCars. So we're finally ready. We've got everything we need. And so BioCars has a goniometer. And so we just 3D printed a kinematic mount for our XYZ stage and brought our kit on a rolling trolley down to BioCars. And basically we took a TTL pulse from BioCars, and that let us know when the laser had flashed, and then we knew to move on to the next position. So it was really nice. Actually, our stuff runs on Epics, and so we could see all our Epics equipment from BioCars, and we wrote a collection software, just a cheap, easy MEDM screen that basically we could interface with BioCars, and that worked fantastically well. Here's the chip, obviously with nothing in it. This is burn paper. This is us testing. And you can see we're burning the paper, and every now and again, you'll see a flash like that. That's the laser light versus the X-ray light, which is burning the paper. And here's that burn paper. BioCars has a laser, which is different from anything else at the synchrotron. So it turns out doing X, Y, and Z is quite hard, but as soon as you add time in there, everything just gets that. It's not like adding one dimension. It's like doubling or tripling the dimensions. It's adding that time dimension actually makes things significantly more complicated. We worked it all out, but there was a learning period where, one of the things we failed to do we didn't leave enough time to move for a couple of our positions. So we did 3 experiments spanning, I think, 7 days. I think we did over 100 chips, and I think a good 20 of those chips we failed at for not allowing enough time. We figured it out halfway through and adjusted and got those time points, but there was that extra bit of thought. This is the real Alex. He also does the data collection. This is Alex at BioCars. All these crystals were grown by Mateusz. Oh yeah, this is you can see here, I don't know if you can see my mouse. If you see the vertical step size, the rightmost column in the table, you can see that the vertical step size changes because as you plow the field, when you get back to that underneath the first position, it's a couple of seconds later, and the zinc cage has time to diffuse. And so there might be zinc free that got there not in the time from the laser, but from just moving through the liquid. So the more time it took to get around back to where you are, you have to leave a bigger step. So the more chips the longer the time step with the laser delay, the longer, the bigger step you have to make vertically. This is one of the downsides of using the nylon mesh. This would be a perfect experiment for the silicon chip. Like the nylon mesh is perfect for 19ID, but the silicon chip would have been perfect for BioCars. And all these experiments could have been done, I think, within 4 or 5 hours instead of 7 or 8 days, had we used silicon chips. And here you can see, I think the chips were named after birds by the look of it for this experiment. And you can see we had a priorities list and what we expected to see. And it was just a mind-blowing success. It was one of the best experiments I've been with. And I would like to tell you more about the protein, but I don't have permission to talk about it. But I can tell you two small things, maybe 3. So this is the protein with no laser and no zinc, so no surprises there. And here we see 1 zinc show up. I told you earlier that we used EDTA to rip the zinc out, and we had one that was harder to rip out. This has a higher affinity. So this is that zinc that has the higher affinity. It's actually under 10 milliseconds after the zinc's released. This first zinc's already in position. It takes like another 10 or 20 milliseconds for the second zinc to show up. And then after that, almost immediately after that, in fact, the substrate shows up and starts doing its little bit of chemistry. And we are making a molecular movie, and we have sort of 20 different PDBs being put into the PDB right now, but I can't actually discuss this because we're publishing it, and I don't have permission. But yeah, so that is the end of my slides. So that is the story of going through diamond serial crystallography, where nylon meshes are fantastic and appropriate for synchrotron X-rays. But if you want to do laser timed experiments, maybe switch back to the silicon. You can do it with nylon. It's quick and it's dirty. You just need a lot of beam time. But biocars I'm genuinely impressed with just how easy it was to actually mesh into biocars and just do experiments there. And I'm really happy to talk favorably about biocars anytime.